So this video gives generating functions for integer partitions of n. This is a nice topic. So here's our first theorem. This is the generating function for all integer partitions of n with k or fewer parts. I'm keeping track of the number of parts with the exponent of y, and I'm keeping track of the size of the integer partition with powers of x. So for example, if I had an integer partition of 10 with 7 parts, that would correspond to a y to the 7th power x to the 10th power in this expression. So the theorem is that this generating function, which gives me information about integer partitions, is given by this expression here. Now, if you haven't seen this notation before, this is a capital pi, and it means to multiply all these terms together instead of summing them if I wrote a capital sigma. So let's prove this theorem. The proof really just comes from expanding each term in this product as a geometric series. So we see that the generating function we have here expanded as a geometric series. So what I'm saying is 1 over 1 minus yx. That's the geometric series 1 plus yx to the first power plus yx to the second power, and so on. The second term, the 1 over 1 minus yx squared, that's another geometric series, but it's a geometric series in yx squared. So I get 1 plus yx squared to the first plus yx squared squared, and so on. And this keeps going until I get the last term in my product, which would be expanded as a geometric series, 1 plus yx to the k power to the first plus yx k power squared, and so on. So that's the generating function we have. And I'm going to think about expanding this, multiplying everything out, and getting all the terms in the expansion. So the terms in the expansion are, in this first parentheses, I get to select some power of yx. So this first parentheses gives me some power. Let's say it's a1 of yx. This second parentheses, when I expand everything out, will give me a term of the form yx squared to the a2 power. And I get everything until the last term, which would be some power of yx to the k. So this is the terms in the expansion. If I simplify this a little bit, I get y to the a1 plus a2 plus a3 up to ak exponent. And the exponent on x is 1a1 plus 2a2 all the way up until I get to kak. This really is, in disguised form, an integer partition in multiplicative notation. So this gives me my lambda, where I'm going to use the multiplicative notation 1 a1 times, 2 a2 times, 3 a3 times, up to k ak times. So using the multiplicative notation for an integer partition, I see that these exponents in x correspond to each integer partition. You give me different exponents a1, a2, a3, I'll give you a different integer partition. So this gives me an integer partition in multiplicative notation. And how many parts are in the integer partition? How many integers are in there? Well, a1 plus a2 plus a3, that's the exponent on y. So this is the integer partition, and this is the length of the integer partition. That actually ends the proof. So that's actually the proof of the theorem. All I really did was take each term in this product, expand as a geometric series, and then think about what I get when I multiply terms in those series together, I get this kind of expression, which corresponds exactly to exponents that have integer or correspond to integer partitions. So x is the length of the integer partition, and y is the length, and x is the size of the integer partition. Okay, so that is a generating function for integer partitions. And since I think these kind of products are uncomfortable at first, I'd like to do two more theorems playing with this idea. So here is a theorem. The product, I going from 1 to infinity, of 1 over 1 minus yx to the I power, that's going to equal the sum, n going from 0 to infinity, y to the n, x to the n, divided by 1 minus x times 1 minus x squared until I get to 1 minus x to the n power. Okay, so let's prove this. Now, if we weren't in a course on combinatorics or discrete mathematics, and you were handed this identity that this infinite product is equal to this infinite sum, it may not be instantly apparent that you're having anything to do with integer partitions. But if you interpret both sides combinatorially, so if you interpret both sides as counting something or understanding integer partitions in some way, then the theorem actually becomes easier to prove. So this is a technique that can be used in not just discrete mathematics. So if I look at the left side, it's actually the same expression I have here in our previous theorem, with the exception that I have an infinity here instead of a k. That would mean that my generating function is for all integer partitions without a restriction on the length. So the length could be anything if I have an infinity up here, because I'm not going to, have this restriction anymore. So the left side counts all possible integer partitions where the power of y gives me the length of the integer partition, and the power of x gives me the size of the integer partition. So I want the right side of the equation to do the same thing. I want the right side of the equation to be a generating function for all integer partitions where the power of y gives me the length and the power of x gives me the size. So I'm going to do that in the following way. So I'm going to consider creating, or maybe I'm going to even sort integer partitions by their length. And here's what I mean by that. You can create any integer partition in the following way. You first pick an n. So you first pick an n. So I'm going to say n is equal to whatever. So you pick a value n. And say that your integer partition lambda must have n parts. So to create any integer partition, I'm first going to pick its height, its length, its height if I draw the Young diagram in French notation. So I have maybe n cells, and I'm going to say, I'm going to create an integer partition, and I want the height to be exactly n. After you create an integer partition, and you say that the height is n, you then have to fill out the rest of it. There's a depiction of an integer partition maybe, by inserting more cells to the right of this initial first column. So to create any integer partition, I'm going to create a column of length n, where n could be any number. And after I create the height of that first column, I'm then going to fill out the rest of the integer partition. Let's call that remaining part lambda. That's what this right side actually is doing. Check it out. Y to the n power. Y is the length of the integer partition. So if I'm saying that the length is n, then I want y to the n power. Y to the n power. X counts the total number of cells in my integer partition. If I say that the first column has height n, then there has to be n cells in there. So this accounts for the length, and this accounts for the cells in the first column. Then, if you imagine multiplying by a 1 here, this circled part is actually the generating function we have in our original theorem, except I'm taking y to be 1. So I'm not keeping track of the length of the remaining integer partition. I'm saying just give me any integer partition you want as long as the length is less than or equal to n. So this circled part gives me lambda with the length of lambda less than or equal to n, which is what I need to fill out everything to the right of the integer partition. So that's all I'm actually going to describe here. I'm not going to write out all the details in this video. Hopefully I'm getting the point across though. The left side is all integer partitions, where y gives me the height and x gives me the number of cells. The right side of the equation does the same thing. It constructs any integer partition by first sorting by length. So you're first going to say how high you want it to be. That's the x to the n, y to the n terms. And after you pick its height, you can fill out the rest by slapping an integer partition to the right. You just don't want that integer partition to be taller than your first column. So you have this restriction. You get that generating function from the original theorem. Let's do one more to finish out this video. These are kind of fun. So let's do one more theorem that's similar to this. So here's a theorem. Let's see if you can catch what we're doing here. So the product, I going from 1 to infinity, of 1 over 1 minus x to the I is equal to the sum, n going from 0 to infinity, of x to the n squared times 1 minus x all the way up until I get to 1 minus x to the n, 1 minus x till I get to 1 minus x to the n. So, what do I have on the left? The left is my generating function for integer partitions, except I guess I'm taking y equals 1. In this example, I'm not too interested about keeping track of the length or the height of the integer partition when I draw the Young diagram. So this just gives me the generating function for all integer partitions of n, right here. This side, the right side, should give me the same thing. This, hopefully, will be a generating function for all possible integer partitions where the power on x gives me the number of cells in my Young diagram. So, here's the proof. I'm going to create any integer partition by first drawing the largest square that can fit inside an integer partition. So create any integer partition this way. I don't think I'm going to describe in words what I'm going to do. I think on page, I think I'll just describe them out loud. So here's what I'm going to do. First, I'm going to create an integer partition by drawing a square of side n. So this is going to be an n by n square. After you draw this n by n square, to the right of the square, so in this region here, draw any integer partition you want, as long as the height is less than or equal to n. So you don't want the height to be taller than the height of the square. So draw any integer partition you want like that. Let's call that integer partition lambda. So it's similar to what we just did before, where I'm starting the integer partition with some cells, and then I'm putting the rest of the integer partition to the right. Next, put any integer partition you want on the top of this square, as long as that integer partition doesn't stick out past the width of the square. So put any integer partition you want in this region. So let's call that integer partition mu. So again, the method of construction is to start with an n by n square. After you have that square, put any integer partition you'd like on the right, as long as the length of lambda is less than or equal to n. Then put any integer partition you want on top, as long as the maximum part of mu is less than or equal to n. So we want the maximum of mu to be less than or equal to n. And as we saw when we discussed integer partitions in our first video, that corresponds to the length of the conjugate partition mu prime less than or equal to n. Any integer partition you like can be created this way, and that's exactly what's counted by this sum. X to the n squared power, that accounts for the n squared cells here. Then I have 1 over this product, as we've seen. That gives me an integer partition lambda with less than or equal to n parts, and I actually have another one. That gives me mu. So this gives me my lambda, and this gives me my mu. And so I'm counting all integer partitions in two different ways. These sums have to be exactly the same. Okay, wonderful.